Welcome back for yet more mathematics. Okay, so this is about inverse trig. Inverse trig derivative intro? Okay. So it's like this. It's like if you have something like the inverse sine of x, how do we find its derivative? That's what this is all about. And the idea is you want to manipulate this thing in such a way that you can use stuff you already know. Okay, so in particular, what I'm going to do is I'm going to take the regular sine of both sides and these are inverse on the right side here. These are inverse functions of each other. So we wind up with the following. That basically the sine of y equals x. Okay, and then the only thing you have to keep in mind is that y can only be from pi over 2 to negative pi over 2. And this is like a pre-cal thing. I'm not going to go into detail about it here, but if anyone would like me to make a separate video going into detail about that, I don't mind. But yeah, keep that in mind. Anyway, so now we have a regular trig expression. And, oh man, I started at the bottom. Ugh. Okay, all the way up here. I'm just going to write down the last thing I wrote down. Sine y equals x. Okay. So now, since we're armed with the skill of implicit derivatives, we can actually take the derivative of this thing now. So, just like we've been doing, I'm going to apply d by dx to both sides. Okay? And dx, we know what that is. We know dx is 1. And now this one, right? So again, remember, y is a function of x. So if we change x, we change y. So the outermost function here, using our chain rule, the outermost function is sine. So the derivative of sine, cosine. So that's the outermost function that we've dealt with. And now go in here, cosine y, and then the derivative of the variable y with respect to x, dy dx. So here we go. Just like that. Okay, cool. So now we can solve for dy dx, and we get this. Dy dx equals 1 over cosine y. Now, here's the thing, this is completely correct. But on the right side, we have the variable y, and if possible, we want to write this thing in terms of x. And we can actually do that because we have this, that sine y equals x. Yeah? So what that means is there's an angle called y, and the sine of that angle is x. It's like x over 1. Okay, so, here's what this means. Set up a triangle. This angle, it looks like 45 degrees, but it's y. The angle's y. And we know that the sine is x over 1. And let's remember what sine is, right? It's the sort of the y component over the r component, or the opposite over hypotenuse, right? So opposite is going to be the x, and hypotenuse is going to be the 1. Okay? So, okay, cool. Well, we need the cosine. We need the cosine. We have the sine, we need the cosine. And if we need the cosine, we need to get this guy down here. Okay? Thankfully, we have a right triangle, so that's no big deal. We can just use the Pythagorean theorem, right? So we basically have something we don't know squared plus x squared equals 1 squared, which is just 1, right? So we can solve for our little blank here. So blank squared equals 1 minus x squared if I subtract x squared from both sides. And then if I take a square root, I get that, the blank equals plus or minus the square root of 1 minus x squared. Okay, now down here, I said y has to be between negative pi over 2 and pi over 2, right? So let's remember what this means from pre-cal. Negative pi over 2 is down here. To pi over 2, that's up here. So that's, boom. That's these two quadrants, okay? Now notice these two quadrants, x is positive or 0. To say that more efficiently, x is never negative in these quadrants, okay? X is greater than or equal to 0, okay? That's important because it allows us to reject the negative here, okay? So we get that our blank is the positive square root of 1 minus x squared. Okay, awesome. So then we get, okay, that's the x component of the triangle. So the cosine of this angle is going to be the blank over the hypotenuse, and the hypotenuse is just 1. Okay? So we get this, that cosine of y equals the blank over the hypotenuse, which winds up just being the blank, which is just the square root of 1 minus x squared. All right. So there we go, right? So we get dy dx equals 1 over the square root of 1 minus x squared, which is pretty crazy. I did not expect this result when I first encountered this function and first learned this material. Pretty crazy result, if you ask me. Okay. So good. So there's that. Now let's take this and generalize it now, okay? This whole process is going to be exactly the same, except let's suppose instead of y equals the inverse sine of regular x, which was all the way down here, instead of this, let's generalize it, and let's say, well, what if we have y equals the inverse sine of some function? So in other words, chain rule, right? So instead of x being in the parentheses of the inverse sine, we have u, which is just any function. U is in the parentheses. Okay? So basically just swap out x with u, but then don't forget the chain rule. Okay? So here's what I'm saying. In general, the derivative of the inverse sine is going to be 1 over, and here's how I think about it, 1 over the square root of 1 minus whatever's inside, squared. Okay? 1 over the square root of 1 minus u squared times, and then go inside, right? This is the inverse sine part. That's what we did here. Then chain rule. Don't forget the chain rule. Go inside, u, right? du dx. Okay? So this is the full derivative of the inverse sine of anything. Okay? And good. So there's that. And I might do another one of these, but really I want you guys to try the others using the same type of reasoning that I set up here. And the places of these is going to change a little bit, but if you understood this reasoning, I want you to try to apply this reasoning to all of the other trig functions. Okay. So there we go. Blair out.